everyone. I wanted to take a look at a different problem from section 3.4, which deals with rational functions. This time you are going to be presented the graph of a rational function, and you're going to be asked to create what that rational function is going to look like. So as you can see on the left-hand side of the screen, I kind of have a checklist already set up, and it's similar to the one that we had used when we were going in the reverse direction, so when I gave you a rational function and you were asked to create a rough sketch. What I want you to keep in mind is when we are building this rational function, it's only going to be an estimate of what it's going to be. It may not be exact. So the problem that we're going to take a look at is similar to the one that is located in the upper right-hand corner of the handout that I provided for you in class. So if you have that readily on hand, please go ahead and pause the video and grab it. Okay, so now that you have the worksheet in front of you, what I want you to go ahead and do is follow along. And so the first thing that I would suggest doing is check to see if there are any holes in the graph. Remember that if there are any holes, that kind of tells us right away if there should be a specific binomial factor that will both occupy the numerator and the denominator. Remember, they would be identical to each other. And actually, looking at this graph that I have here, I don't see any holes, which again are identified as open circles. So in this case, I'm just going to run an X through there and say that there are no holes in this case. So I'm going to move on. So I'm going to go ahead and take a look at my vertical asymptotes, and I see that I have one at x is equal to -3, and I also have one at x is equal to 3. So what we're going to go ahead and do now is rewrite these so that they're binomial factors. So the quick way behind this would be to just do x and then the opposite sign of that number. So if you have x is equal to -3, that becomes x plus 3. We also have x equaling a positive 3, so we would rewrite that binomial factor as x minus 3. One other thing that we want to check would be if these binomial factors have a certain degree or multiplicity attached to them. And we can do that by looking at the short run behavior of the function. So if I take a look at the vertical asymptote that I have on the right, notice that the function itself, the short run behaviors are going in the same direction. So this tells me that my degree is going to be even. And again, since we don't want to get too crazy, we're just going to assume a 2. It's small enough, and since it's the smallest even that we have, and well, not the smallest even, but it's the smallest even that this would be true. Okay, so that is why we're going to use a multiplicity of 2. If we go through here and take a look at the vertical asymptote on the right-hand side, we see the same thing happening. Notice on the left side, the short-run behavior is going down, and on the right side, the short-run behavior is also going down. So again, this tells me that I have a multiplicity of 2. Okay. So that means that we're going to go ahead and drop these in. Remember that your vertical asymptotes are located in the denominator, because this is where the restrictions are set. And remember, one of the restrictions that we have for a rational function, which is essentially like a fraction, is that the denominator can never be equal to 0. And for those areas where that does happen, that's actually where your vertical asymptotes are happening as well. Okay, so we're done with vertical asymptotes. What I'm going to go ahead and say right now is we're going to skip the y-intercept. And my reasoning for this is if you take a look at the image either on the screen or on your worksheet, notice that the y-intercept is not so easily identified. For example, in mine, it looks like it might be at the point 0, positive 1/2. However, if you take a look at the image on your worksheet, it doesn't actually look like it's cutting halfway through. Some people might argue that it's cutting at the point 0, positive 1/4, or maybe even 0, positive 1/3. So for now, since it's a little bit vague and a little bit in the dark, I'm going to skip over the y-intercept and I'm going to move on to my x-intercept. So it looks like I have an x-intercept located at -5. I have another x-intercept located at -1. and then I have yet another one at x is equal to positive 2. So again, the thing that we want to do is we want to rewrite these as binomial factors. So this is going to become x plus 5. This is going to become x plus 1. And this becomes x minus 2. So the next thing that I want us to do is identify what is happening at the x-intercept. Here, it looks like it is just cutting through. So that must mean that we have a multiplicity or a degree of 1 for this binomial factor. If we take a look at the next x-intercept, I'm seeing a bounce. So this tells me that this degree must be a 2. Okay. And again, at this last x-intercept, since I'm doing a cut, I must have a degree or a multiplicity of 1. So I'm going to go ahead and drop these in. So I have x plus 5, x plus 1, and x minus 2. Ooh, and I want to make sure that that's squared because of the bounce. Okay, so what I also want to tell you is it doesn't matter what order you write these in. So you could have had x minus 2, x plus 5, and x plus 1 squared. You could have written it in that order. It's all still correct. So we have identified all of our x-intercepts, so we are good there. So the next thing that we want to go ahead and do is identify this horizontal asymptote. So what I can tell you is, since I do have a horizontal asymptote that is equal to negative 2, that must mean that that the degree on top must be equal to the degree on the bottom. Okay. Recall that if you're not sure as to why, refer back to those 3 rules that we use in order to identify horizontal asymptotes. Remember that the only options you have are no horizontal asymptote, a horizontal asymptote on y is equal to 0, or a horizontal asymptote that is the ratio of the lead coefficient in the numerator over the lead coefficient in the denominator. In this case, we must have the degree on top be equaling to the degree on the bottom because our horizontal asymptote is not 0 or does not exist. So let's double check something really quick. Let's count up the degrees. So it looks like I have a degree of 1 here, a degree of 2 here, and a degree of 1 here. So I have a degree of 4 on top, and then I have a degree of 2 on the bottom and another degree of 2 on the bottom. So that must mean that I also have a degree of 4 on the bottom. So this fits. So this tells me then that my lead coefficient should be a negative 2 over a 1. Okay, so we're actually done with this. Now, to go back to the y-intercept here, I can actually tell you we don't need it anymore. We actually have everything. Remember that we've used the y-intercept to help find what we call A, which is our vertical stretch or compression. But in this case, since we've identified the horizontal asymptote, it already tells us what our lead coefficients need to be. So in situations like this where you are provided the asymptote here, or since an asymptote does exist, you don't need to worry about finding the y-intercept. So again, your final answer is just going to be negative 2 times the quantity of x plus 5 times the quantity of x plus 1 times the quantity of x minus 2 all over, you could have the 1 in there or you could get rid of it, 1 times the quantity x plus 3 squared times the quantity x minus 3 squared. I hope this was helpful. If you have any questions or need me to explain anything further, please let me know.